Our eyes are our windows on the universe. Throughout our evolution, they have enabled us to observe and make sense of the world around us. And as our understanding has grown, so the questions that we ask about our world have become ever more complex. To help us answer these questions, we have built telescopes to study the vastness of outer space, and microscopes to study the smallest objects in the finest detail. But imagine what we could learn if we were able to build a microscope so powerful that it could look deep inside the very materials from which our world is made. So powerful that it wouldn't just reveal how atoms and molecules are arranged, but how they move and interact with each other, and how they bond together to form metals, alloys, chemicals, plastics, and even the biological substances upon which life itself depends. Such a microscope could unlock the secrets of materials at the atomic level, enabling us to modify and tailor their properties and performance to satisfy the demands of our increasingly technological society. The benefits for medicine, energy production, transport, electronics, manufacturing, and the environment would be immeasurable. It might be a surprise to learn that such microscopes do already exist, and that they are being used every day to help us understand the structure and properties of materials in more detail than ever before. But unlike conventional microscopes, they don't use light and magnifying lenses. Instead, they illuminate the fine structure of the atomic world using the extraordinary quantum physical properties of a subatomic particle, the neutron. Ironically, to visualize nature's smallest objects, we must construct some of the world's largest science facilities to produce the intense beams of neutrons that are necessary for these studies. Neutrons can be produced either by the controlled fission of a nuclear reactor or by spallation, an even more efficient process in which high-energy subatomic particles from a giant accelerator are used to chip off or spall neutrons from the nuclei of heavy atoms within a spallation target. Around the world, such neutron facilities have become vital research tools in the fields of physics, chemistry, biology, engineering, geology, and even paleontology and archaeology. However, it is inevitable that whether using the most powerful telescopes or the most powerful microscopes, the more we see, the more we realize there is to see. And now, as we see the atomic world at the very limits of our existing neutron capabilities, we know there is very much more to be discovered beyond the present neutron horizon. The exciting news is that Europe is about to embark on a voyage of exploration and discovery well beyond the limits of any existing neutron facility. Europe is poised to build one of her most ambitious scientific projects, the European Spallation Source. For almost 2 decades, hundreds of leading European scientists and engineers have developed and refined the design of the European Spallation Source, or ESS, a neutron facility whose beams will be at least a factor of 10 more powerful than any other facility in the world, and a facility that will maintain Europe's global lead at the cutting edge of neutron science well into the 21st century. Let's take a closer look at the ESS design. At the pulsing heart of ESS are 2 ion sources, each producing a pulse of positively charged hydrogen atoms, or protons, 16 times every second. The pulses are only 2/1000ths of a second long, but each contains 1,000 million protons. These 2 intense proton pulses are funneled together to create a single pulsed proton beam, which is then injected into a linear particle accelerator 2/3 of a kilometer in length. As the pulsed beam passes along the accelerator, It is focused by a lattice of magnets and steered through a sequence of radio frequency cavities. Each cavity transfers more energy to the protons until they're traveling at almost 90% of the speed of light. The protons leave the linear accelerator with an energy of 1,000 million electron volts, and at the very end of their journey, they smash into a molten metal target. It is in this collision that the spallation process takes place, with each proton spalling approximately 30 neutrons from the nuclei of the atoms inside the target. These high-energy spallation neutrons lose most of their energy and slow down as they repeatedly collide with light hydrogen atoms, which are contained in moderators that are carefully positioned around the spallation target. Beyond the moderators, beam tubes transport the resulting pulses of low energy or thermalized neutrons to an array of advanced instruments and spectrometers located in arcs around the target station. It is with these spectrometers that Europe's multidisciplinary neutron scattering scientists carry out their experiments. The neutrons are scattered by the scientific samples into massive banks of detectors placed around the sample chamber. And because neutrons are such a gentle probe, they don't change or damage the samples in any way. By interpreting the complex patterns into which the neutrons are scattered by the samples, the scientists can reconstruct the positions of the atoms and molecules within the samples. And by measuring the change of velocity of the neutrons as they are scattered, they can extract detailed information on how those atoms and molecules are moving. ESS not only allows this information to be obtained much more quickly than at any other neutron facility in the world, it also provides the information with significantly higher precision. In this respect, ESS is the Hubble telescope of neutron sources, and just as the Hubble telescope allows us to see deep into outer space, ESS will allow us to explore inner space, opening entirely new scientific and technological frontiers in our studies of where atoms are and what atoms do. ESS will cost 1.3 billion euro, and construction will take 7 years. Nevertheless, the socio-economic advantages of hosting this world-leading neutron facility are enormous. Consequently, the competition to provide a site for ESS has been intense. In May 2009, a meeting of European research ministers concluded that Scandinavia's bid to host ESS in the Swedish city of Lund had been the strongest. ESS can and will give European science, technology, and industry a tremendous advantage on the international stage. It will be one of the most important and prestigious scientific research facilities in the world, enabling developments as diverse and as significant as drug design, new magnetic materials for data storage, super strong, super light ceramics for engineering, biocompatible materials for repairing our fragile bodies, hydrogen fuel for clean transport, innovative processes for capturing carbon. The list is endless. But just as exciting are the potential developments that we don't yet know about. ESS is sure to lead to discoveries that will take us completely by surprise. Discoveries that will offer benefits, opportunities, and challenges that we can't yet imagine. Discoveries that will change the way we see our world.